In this video, we'll take a look at centripetal force. Acceleration occurs when an object speeds up, slows down, or changes direction or turns. Acceleration that involves turning or change in direction is referred to as centripetal acceleration. Newton's second law tells us that acceleration is caused by a force. In this case, the force that causes centripetal acceleration is referred to as centripetal force. Centripetal force is defined as a push or pull towards the center of a curve. Centripetal force is not to be confused with centrifugal force. Most people have heard the word centrifugal force before. Centrifugal force is a perceived force. It's that feeling that you're being pushed towards the outside of a curve whenever you're turning. Say you're riding in a car, you're driving a car, and you turn the car to the right. You feel as if you're being pushed to the left into the door. That feeling of being pushed to the left into the door is referred to as centrifugal force. What that is a result of is your inertia. Newton's first law tells us an object in motion tends to stay in motion, an object at rest tends to stay at rest unless a net force acts upon it. When the car turns, your body is a body in motion, and what your body tries to do is continue to move forward in a straight line. So the tires turn the car, not you. The car starts to turn to the right, your body wants to continue forward until it meets up with the door. The door then pushes you towards the inside of the curve. The door produces a centripetal force that causes your body to turn. So that feeling of being pushed towards the outside, that centrifugal force, is just a perceived force. It's a feeling that you get because of your inertia. The actual force is the force of the door pushing you towards the center of the curve, and that is centripetal force. As for the car, again, it's the friction between the tires and the car that produce that centripetal force. When you angle the wheels of the car, there is a component of the force being produced by those wheels that points directly towards the center of the curve, and it's that friction that causes the car itself to turn. The amount of centripetal force needed depends on the mass of the object, its tangential velocity, and the radius of the curve. Mass and centripetal force are directly proportional. In other words, the more mass an object has, the more force it requires to make that object turn. Doubling the mass would double the amount of centripetal force needed to turn that object. Having the mass would half the amount of the centripetal force needed to turn the object. They are a directly proportional relationship. So they change in exactly the same way. 4 times the mass would require 4 times the centripetal force. 1/4 the mass would require 1/4 the centripetal force. The changes are identical, it is a directly proportional relationship. A good real-world example of this, a good real-world scenario involving this is to look at the tires on trucks and cars. Truck tires are much larger than car tires, and this is because trucks have more mass than cars do. It requires a much greater force to turn a truck than it does to turn a car. As a result, you need a larger tire patch in contact with the road to produce a greater amount of friction in order to turn that truck. Radius and centripetal force are inversely proportional. This means they change in the opposite way. This is due to the steepness of the curve. A curve with a short radius has a very steep curve. The amount that the direction has to change in this little area here is much greater than the direction has to change in this section, involving roughly the same angle. So if I want to go through 30 degrees of motion on this small radius curve, the direction has to change quite a bit. That's due to the small circumference. If I go through a 30-degree range of motion In this much larger radius curve, my directional change is much less. It's a much flatter section through here than it is through here. I mean, this plays into the flat Earth argument. A lot of flat earthers say, well, I stood on Paris Mountain, and when I looked at Greenville, it looked like it was flat between Paris Mountain and Greenville. And of course, it's going to look that way because the radius of the Earth is huge. So, for that tiny little angle of displacement, that portion of the curve is going to be almost flat. And so you're not going to be able to see it. You're not going to recognize the curve. The larger the radius, the flatter that section of the curve becomes. Because small radius turns are steeper, it is going to require a stronger centripetal force to get the object to change that direction much quicker. Again, the small radius curve produces a small circumference, which involves a pretty steep curve, pretty sharp curve. The object has to change direction faster, so you're going to need a greater centripetal force to get that done. A longer radius curve is flatter, therefore requires less force to change the object's direction. So again, we're not going to have to change our direction as much, and because of that, we're going to need less force. We should be able to see this if we draw some lines on here for the tangential velocities. And we can see specifically how far those tangential velocities have to change. This is by no means a perfect illustration because the small circle is pretty small. But when we look at how much the tangential velocities have to change, it is a much smaller change through this, I'm estimating about 30-degree angle, on the large radius curve than it is on the small radius curve. We have to change the direction much more significantly there. So small radius turns require stronger centripetal forces due to the larger change in direction that has to happen for every degree that you're going. The longer radius curves are flatter. They don't need as much centripetal force. And again, you feel this every time you drive. Driving is a great example of physics because we experience so many of these phenomena as we drive a car. In a sharp curve, a very sharp turn, you feel like you're being pushed around more than you do in a long, gradual curve, even at low speeds. I mean, going through both curves at the same speed, you would feel like you were being pushed around more in the sharp curve than you would in the long, gentle curve. So for example, if we had to make a turn like this versus a turn like this, you're going to feel it a lot more here. You're going to feel your body being pushed around more because that turn is steeper. What you're feeling is the centripetal force. In that sharp curve, it takes more centripetal force to change your body's motion, and you just feel that. In a long, gradual curve, and this is like turning on from one road to another, turning off of 17 onto Carolina Parkway, for example. That's a sharp turn. This is like the turns you feel on I-26 that are long, gradual curves. You don't feel it as much there because it doesn't take as much centripetal force to turn you on those long, gradual curves. Finally, the most complicated one, that's the velocity of the object. And the relationship is a little different. It's not a directly proportional relationship. It's not an inversely proportional relationship. It's more of a direct quadratic relationship between velocity and centripetal force. In a quadratic relationship, one of the two variables is squared, and the one that is squared in this case is going to be the centripetal force. Okay, and this applies to how they change. And that's all we're talking about here is how they'll change. If we were to double the velocity, 2 times the velocity, the change in centripetal force would be 2 squared, or 4 times greater. Twice the velocity gives us a 4 times greater centripetal force requirement. And again, that is just doubling, not doubling, squaring the change that we made to the velocity. The velocity is doubled, so the centripetal force would be 2 squared, 4 times greater. If we tripled the velocity, had 3 times the velocity, it's going to be 3 squared for the centripetal force, or 9 times the centripetal force needed to turn that object. Again, whatever we do to the velocity, we're going to square that for the centripetal force. If we cut the velocity in half, it'll be 1/2 squared for the centripetal force, or 1/4. So whatever we do to the velocity, we have to square that for the centripetal force. This really makes velocity the most significant factor in determining how much centripetal force is going to be required. Changes to it causes bigger changes to the actual centripetal force. Slowing down a car just a little bit reduces the centripetal force more than reducing the mass in a greater way. So again, if I wanted to, for example, cut the velocity of a car in half, that has a greater effect than cutting the mass of the car in half. Okay, it would be 4 times the effect, 4 times the 1/4 the centripetal force required, whereas cutting the mass in half would just be 1/2. The velocity has a bigger impact on the centripetal force than either the mass or the radius. And again, driving produces many examples of it. It's a great way of understanding physics. When you take a turn slowly, even a sharp one, you don't feel the centripetal force as much. If you go flying into that curve, on the other hand, you feel like you're being thrown around a lot more. The forces you experience are much greater because the centripetal force needed to turn your body is much greater. And again, that velocity has an even bigger impact than mass or radius does. So these are the 3 relationships. Mass and centripetal force are directly proportional. That means mass has to go in the numerator of our equation. Radius and centripetal force are inversely proportional. That means it has to go in the denominator. And velocity and centripetal force have a quadratic relationship, and it's a direct quadratic relationship. Because it's direct, it'll go in the numerator and it will be squared. So taking all these ideas in mind, that's where the equation comes from. Centripetal force is equal to the mass of the object times the tangential velocity squared divided by the radius. The velocity is a tangential velocity, not the angular type, for this particular equation anyways. And it needs to be in meters per second. The mass would need to be in kilograms, and the radius should be in meters. Whenever we do this calculation, again, velocity is tangential, and it should be meters per second. So if you had to calculate it, for example, you would use the tangential velocity equation, not the angular velocity equation. There is a different equation for centripetal force that uses angular velocity, but the only one we're going to talk about is this one. Your masses need to be in kilograms, so if they're not in kilograms, you would need to convert it. And your radius would be in meters again. If it's not, you have to convert it. That is all for unit cancellation. If our mass is in kilograms and we're multiplying it by meters per second squared, we would get meters squared per second squared. And if our radius is in meters, what ends up happening is this meters will cancel out one of these. And since this is in the denominator, it's going to move down. And we end up with kilograms meters per second squared, which is the force unit, newtons. So again, you have to have these in the correct units so that you can calculate a force in newtons. Let's take a little bit of a look at the math here to understand those relationships again and see how those relationships actually work. A 0.2 kilogram ball is tied to the end of a 1 meter string. The ball is swung with a velocity of 4.5 meters per second. What is the centripetal force exerted by this string? So the mass of our ball, that's the 0.2 kilograms. 1 meter would be the radius, and it would be a radius because we would hold the string and swing the ball. Our hand, where we're holding the string, would be the center of rotation, so it is from our hand to the outside edge of the circle. So that is a radius. Swung with a velocity of 4.5 meters per second, that is tangential. And the reason I know it's tangential is because it's in meters per second. If it would have been an angular velocity, it would have been degrees per second, radians per second, or revolutions per second. Because it's meters per second, I know that is a tangential velocity. I need to know what the centripetal force is. The equation that has these four things in it, the only centripetal force equation that I'll be covering in this video, is this: mass times the tangential velocity squared divided by radius. Substitute everything in. 0.2 kilograms was our mass, 4.5 meters per second is our velocity. Don't forget to square it. Our radius is 1 meter. 0.2 times 4.5 squared equals, divided by 1 is 4.05 newtons. And I always do that. I will do the math in my numerator, and I will hit the equal sign on my calculator after I'm done with it, and then hit divided by, because I just want things to work in the correct order of operations. I don't use a fancy scientific or graphing calculator when I do my math, and it does sometimes do things out of order. Even the graphing ones do. So just to be sure, I'll do 0.2 kilograms times 4.5 meters per second squared equals, divided by 1. So that is our first problem. Let's take a look at the second one. And in the second one, what we're going to do is change the mass of the ball. In our first calculation, the mass is 0.2 kilograms. In the second calculation, it's 0.4. Everything else is the same. I have doubled the mass. And according to my relationships, if my equation is correct, if I double the mass, I should double the centripetal force that that string has to produce. Let's see if it works. Again, the mass is 0.4 kilograms, the radius 1 meter, the velocity is tangential, is 4.5 meters per second. We're looking for the centripetal force using the same equation. Only thing that's changed is the mass is now 0.4 kilograms. 0.4 times 4.5 squared equals, divided by 1 is 8.1 newtons. So what we're seeing is a doubling of the mass, started off at 4.05, giving us a doubling of the centripetal force. When we double the mass, we double the centripetal force, a directly proportional relationship. So again, that's in the equation. That relationship is built into the math. That's how the equation was derived. Take a look at this one. We're going to build on the one before it. If you'll notice, I'm changing the radius. So we're going to keep the 0.4 kilograms, and I'm going to change the radius of the string to 0.5 meters. Still have our same mass, 0.4 kilograms. Our radius has changed to 0.5 meters, and my tangential velocity is still 4.5 meters per second. Still looking for centripetal force. And again, the only thing that's changed from this calculation to the previous one is the radius. I cut my radius in half. Again, the relationship is inversely proportional. I started off with 8.1. If it's a true inversely proportional relationship, that centripetal force should double. Cutting my radius in half should double my centripetal force. And when you do the math, that is indeed what happens. We end up with 16.2 newtons. Went from 8.1 to 16.2. Cutting the radius in half doubled the centripetal force. And again, that's how these equations are derived. You look at the relationships and you take those relationships and you stick them into an equation. Directly proportional relationships go in numerators, inversely proportional relationships go in denominators. Now this velocity one, this is the first time we've seen one of these where we have to square this unit, square this variable, and that's what gives us that quadratic relationship. Let's play with that one. So from here to here, I'm changing the velocity. 4.5 meters per second to 9. I'm doubling the velocity this time. The other two numbers are going to be the same as they were in the previous example. Doubling the velocity, 2 times the velocity, should give us 2 squared, or 4 times the centripetal force. Let's see if that happens. Again, everything's the same here except for that tangential velocity. We're still looking for centripetal force. It is still mvt squared over r. Again, I changed that velocity now. I doubled the velocity. I should see 4 times the centripetal force. 0.4 times 9 equals, divided by 0.5 is 64 point, exactly 4 times the centripetal force. So all those relationships are there. If you're ever answering a conceptual question that gives you this theoretical situation where you're tripling this or having that, and you don't remember what the relationships are, you can't remember if they were directly proportional, inversely proportional, quadratic, or whatever, play with the equation. The equation's got those relationships built into it. Of course, all 4 of these have been just using standard calculations, no algebra, no unit conversions, no extra steps. You are expected to be able to work these kinds of equations algebraically. I should be able to give you the centripetal force and the velocity and the radius and have you find the mass, or ask you to find the radius for me if I give you the force, the mass, and the velocity. Remember, if you're looking for radius, you have to move it out of the denominator first. Multiply by both sides by r before you do anything else. You solve. The basic algebra is still there. I'm not going to do one of the basic algebra types. Instead, I'm going to do one of the multi-step types where you have to go back to old equations to figure out information for this. And we're just going to build on the equations that we learned with the velocity part of this, with the tangential and angular velocity. Specifically, the tangential one, because that's the one that's in this particular equation that we're learning. 1,500 kilograms, that is the mass of the car. 30 degrees. Degrees, radians, and revolutions, that's an angular displacement, theta. 30-meter radius, 2.5 seconds, that would be a time. So I have a mass, I have an angular displacement, I have a radius, and I have a time. And I need to know what centripetal force is. Now, thinking about the centripetal force equation, I need mass, got it. I need tangential velocity, don't got it. And I need radius, have that. So I'm missing this tangential velocity. So I have to do the math that I taught you in the tangential and angular velocity parts to figure out what VT is before you can solve this. Now, whenever doing a tangential velocity, I need my angular displacement to be in radians, because radians is the one thing that relates together the radius and circumference of a circle. Whereas if I know the radians and I know the radius, I can figure out what the arc length is, the area of the circumference that I'm going to travel through. Degrees doesn't do that, and revolutions doesn't do that. You've got to have radians for theta in order to get that relationship that will allow you to calculate arc length. Again, this is the equation, theta equals arc length over radius. Theta must be in radians. So the first thing I'll do is I'll convert the 30 degrees into radians. It's a dimensional analysis kind of conversion. My equivalence for radians and degrees is 2 pi radians. That's one complete circle in radians. A complete circle is 2 pi. So 2 pi radians equals 360 degrees. That's a full circle in degrees. Basically, that's a full circle in radians. That's a full circle in degrees. I set it up as 2 pi radians over 360 because I need to get the degrees to cancel. So the 360 goes in the bottom in this case. If I had started with radians and wanted degrees, the radians would have gone on the bottom. I have to multiply and divide 30 times 2 pi equals, divided by 360 is 0.52 radians. Once I've got that, I can go into this angular displacement equation, substitute 0.25 radians, that's theta, equals s over 30, the radius, multiply by 30 on both sides to solve. 0.52 times 30 is 15.6. And again, your unit for your arc length will be identical to whatever your unit for your radius was. Because my radius was in meters, my Arc length is also in meters. Radius is just the relationship between the two. Now I can go into the tangential velocity calculation. Tangential velocity is equal to arc length divided by time. Arc length is 15.6 meters times 2.5 seconds. 15.6 divided by 2.5 is 6.24 meters per second, just what you see in the equation. So that's the tangential velocity. Now that I have that, again, I've got to have mass, tangential velocity, and radius to do my centripetal force. I've got my mass, it's 1500. I've got my tangential velocity at 6.24 meters per second. And I've got my radius, it's 30 meters. Substitute. Simplify, I'll do the 1500 times 6.24 squared first. And again, that's the way I always do it in the calculator. I just get that math done first, make sure I have an answer showing up on my calculator display. That'd be 58,406.4. And then I'll divide by 30. That way I make sure that I'm getting the right thing squared, that I'm dividing the right things. It just makes sense to get that equal sign in there first and then divide. Be 1,947 newtons. Much higher than our previous examples because we're dealing with a car this time, and it has that much greater mass. There is another way of calculating centripetal force using the angular velocity equation, but I'm not going to get into that.